In Bitcoin, transactions are the primary means by which money and data are represented within the blockchain. Today we will look at the structure of a transaction and the relationship between transactions. A transaction consists of one or more inputs, one or more outputs, a lock time value, and a version number. The input of a transaction is also referred to as the spending condition. A transaction input can be thought of as a key that fits a very particular lock. The output of a transaction is also referred to as the locking condition. A transaction output can be thought of as a lock that can only be opened with a very particular key. The lock time value of a transaction is used to govern the future date at which a transaction will become valid for acceptance into the Bitcoin network. A transaction that has a lock time in the future is like a future dated check which the bank will not accept until after the indicated date on the check. Transactions do not exist in isolation, however, and the input and output values only have meaning when considering two or more transactions. The relationship between an input and an output is that a transaction input is created in order to unlock or spend the output from a previous transaction. In this manner, the inputs and outputs form an alternating chain of locking and spending conditions. At the head of this chain, there exists an output for which there does not yet exist a transaction containing a spending input. This transaction output is referred to as a UTXO, or unspent transaction output. We will now peer a little deeper into the internals of a transaction input. The transaction input data structure consists of several fields. The first two fields form part of the linking structure between transactions. The transaction ID field references the transaction ID of the transaction that contains the output this input is spending. In our previous example, if this input is inside a transaction B, then this field will contain the transaction ID of transaction A. Similarly for the next field, which contains the index of the output in the transaction this input spends from. Notice that these two values combined form a primary key of sorts. That uniquely references the transaction output where this input is spending from. The next field is the sequence number. The sequence number is essentially a flag that activates the lock time value of a transaction. This is of particular use in payment channels. The Bitcoin script field is the last field, and this contains the programmatic conditions that form part of the locking and unlocking behavior of transactions. We previously used the analogy of a lock and key to describe input and output behavior. This Bitcoin script field is the programmatic key that must be provided to unlock its corresponding UTXO. The transaction output is the simplest of the data structures. It contains only two fields. The first field specifies the amount of satoshis or units of Bitcoin that this output is locking up. The Bitcoin script field sets the locking conditions for this output. This forms the lock to some input's key that will in future be able to spend this output. The Bitcoin script in the output of a transaction is also known as the script pub key for historical reasons. Now let's take a look at Bitcoin script. The Bitcoin script interpreter consists of a processor, which is not 100% accurate, but for our example, having a processor as a logical construct will assist in our understanding. A program supplied by you, the developer, two stacks, a main or default stack, and an alternate stack, also known as the alt stack. This is also where this channel gets its name from, by the way. Two stacks. Combined with the Bitcoin script interpreter's finite state machine architecture, this makes the script interpreter what is known as a two-stack pushdown automata. Let us now consider how the script interpreter evaluates a program. Consider this program. This one consists of one chunk of data, followed by an op-dup operator, followed by one op-drop operator. When the script interpreter starts, the instruction pointer points to the data. The interpreter pushes the data onto the main stack. This is what the interpreter normally does with data. Data gets pushed onto the stack. The instruction pointer advances and the interpreter encounters an operator. The operator is evaluated by the processor. In this case, the op-dupe operator creates a copy of the topmost data item in the stack and pushes that copy onto the stack. As you can see, our stack now contains 2 bits of data. The instruction pointer moves to the first op-drop. The op-drop operator is now evaluated by the processor, causing the topmost value of the stack to be discarded. Our instruction pointer reaches the end of the program and the program halts. The script interpreter will return a Boolean value depending on what is contained within the topmost value of the stack. A true value is represented by a value of 1 in the topmost value in the stack, which is the case for us. Had the topmost value been a 0, the program would have interpreted that as a return value of false for the program. In the case where data is left on the stack, a byte vector of all zeros is interpreted as false, and any other data that doesn't consist of a all 0 byte vector is interpreted as a true result. This predicate logic forms the core of the Bitcoin script interpreter.